Cool. Very honored to be here. And today I'm going to talk about the response of Southern Ocean to climatological iceberg freshwater forcing. So we're going to start from some of the background information. So the Antarctic melted water can be divided into two components. And the first is basal melt, which is under beneath the ice shelf, and also the carved iceberg in front of the ice shelf. So these two components are roughly 50-50 in terms of the amount of fresh water they add into the ocean of the main states. And in this study, we're going to focus on the iceberg melt. So when iceberg has been carved at the front of the ice shelf, so under the effect of the wind and the current, so it will drift around the Antarctic, around the Antarctic and the Southern Ocean, and shows this like a windmill-like pattern. So, and the melting of this drifting iceberg in the Southern Ocean will continuously affect the heat flux as well as the freshwater flux along their trajectory. And lots of the previous model study have proved that this freshwater will have the impact on the Southern Ocean and includes the surface temperature and salinity anomaly as well as the stratification, vertical mixing, and the sea ice extent. However, due to the model priority, currently integrating a dynamic ice shelf ice sheet component into a coupled climate model is still challenging. And so previous models therefore assume the idealized freshwater scenario. And the common practice for the melted water will be either in a spatial uniform forcing, just like a very classical Hosing experiment, or in a spatial vary forcing, but within a very narrow region around the Antarctic. So the bottom figure I show how we apply the Antarctic iceberg melt in ACCESS-NRI, and as you can see, it's just added along the coastline. So this idealized freshwater scenario might be suitable for the basal melt along the coastline, but it definitely cannot appropriately represent the non-uniform distribution of the freshwater released by the iceberg. So if you look at the figure on the right, so top figure I show how we applied iceberg melt in ACCESS-NRI, and bottom I show how it should be in reality. So as mentioned by the literature about the freshwater experiment, so the inappropriate spatial distribution of freshwater can lead to an inaccurate representation of their impact on the Southern Ocean. And then one hypothesis just naturally coming to my mind that could introduce a more realistic distribution of the iceberg melting, reduce the bias in the Southern Ocean or not? And this study will try to answer this question. So, this study we're going to use the ACCESS-NRI with 1 degree resolution, which is the ocean CIS carved model. The ocean we use MON5 and the CIS we use CIS-85. It's all driven by the GRE55. Since we focus on the impact on the main states, so we choose a normal year forcing. And we will have two perturbation experiments. The first is control run, which is exactly the ACCESS-NRI default experiment. So we apply the iceberg melt along the Antarctic coast. Well, we also have another experiment called iceberg, which is exactly the same with control run, but we just redistribute the fresh water from along the coastline to this like a more realistic windmill-like drifting pattern. So we don't change the amount of fresh water, just a spatial distribution. So we start from 1,000 years spin up, and then we run another 100 years and choose lesser 30 years and calculate the main states. That's for the control run, and we do the same thing for the iceberg experiment, but with a drifting iceberg spatial pattern. And then we can just compare the difference between the iceberg experiment and the control run. So here is some of the result. We first show the anomaly as a result in terms of the salinity and temperature. So if you look at the figure on the left, so that's the mean state from the control run. And the figure on the right, we show the anomaly at surface salinity as well as the salinity anomaly at subsurface, which is 500 meter depth. And we also do the same for the temperature. So what one can say is there's an overall freshening signal at the surface salinity, and subsurface we saw a softening signal. And we don't see much of the signals in the surface temperature, but we see a quite significant intensified warming at the subsurface. And to further provide more information about that thing, so we also, so to more clearly show the ocean response, we choose two sector and calculate the average and then plot this depth latitude plot. So, and we've got like these two sections, the India section and the Pacific section shows very different result. So if you look at the India section, so we applied more fresh water. So the iceberg experiment shows more fresh water over here, and it's caused like surface freshening as well as surface warming signal. And if you look at the Pacific sector, so the less fresh water along the coastline, and it will cause a softening signal and the subsurface cooling signal. And it also shows the anomaly in terms of density and stratification. So we divided the density anomaly into the anomaly induced by the salinity, which we call haze density, and anomaly induced by the temperature, we call the thermal density. And if you look at the figure on the bottom, so you can clearly say salinity has a dominant impact on the density change, and that really makes sense because in the high latitudes, the temperature change range is really limited. And it also shows using n squared to represent the stratification. And so you can see in the Indian section, we have like increasing risk n squared to represent a more stable of the water column, and in the Pacific sector, it's on the contrary. All right, then we have like more clearly understanding about this chain of response of the ocean to the fresh water forcing. So in the Indian section, we have more fresh water. Then we have like reduced surface salinity and the density, so will cause like a stratification, and this will surprise the diffusive like heat flux from warmer subsurface to colder surface, and that's why heat will accumulate below the 200 meters. That's why we have this subsurface warming. And in Pacific sector, we have less fresh water along the coastline. This will cause like a decreased vertical stratification and enhance the mixing. This is why we got like subsurface cooling signal here. And you might know that we don't see much of the temperature anomaly at the surface, and that's induced by the sea ice feedback. And due to the limitation of this talk, we're gonna skip this segment. All right, let's just go back to the hypothesis, like a few figures I show. So could introduce a more realistic distribution of iceberg reduce the bias in the Southern Ocean? And the quick answer is yes. So here I shows the left eye shows accessible bias, and the left shows our model study improvement. So the left eye, to keep the consistent, I shows in the left I shows the WA13 minus control run. Again, this is the mean state, and from the right I shows iceberg minus control run. So and then you can see very similar patterns that in the India sections, they have like surface freshening, subsurface softening, and subsurface warming. As well for the Pacific sector, you have like along the coastline, there's a softening signal at the surface and subsurface cooling signal. So to know that the color bar on the right is 103 along the left. So when you say there's a comparable pattern, that represents a reduce of the bias up to 30%. Therefore, we suggest it is necessary to incorporate accurate representation of the Antarctic meltwater in the model simulation, as is one of the significant factors contributing to model bias, especially in the high latitudes. So, of course, ongoing model development will allow the fully coupled ice sheet ice shelf component into the ocean or the climate model. And the MOM6 have planned to do it, and also as mentioned, as discussed by Andy and Felicity this morning, our ACCESS model has planned to do it, but it takes some time. However, there's still lots of things we can do to minimize the bias induced by the fresh water before this active or the dynamic ice shelf ice sheet component being applied. So the first thing is the spatial, or we call the horizontal distribution of the meltwater. So as highlighted by this study, so we need to apply it in a more realistic way rather than just along the coastline. And then also for the vertical distribution, so it's more like for the basal melt, because some of the study has mentioned that the basal melt 80% of the basal melt occurred as top 400 meters, but in our setup, we still add the basal melt as a river, as a surface layer, or like top 40 meters. So they will cause like a difference in the surface stratification, and especially for the future scenario, which we applied a huge amount of fresh water into the model. All right, so here's the conclusion. And so we did a very simple work, And our study proves that if you just like prepare a full thing and change one line with the code, and boom, you can reduce the 30% of the bias in the highlighted tubes in terms of mean state of the temperature and the salinity. So it is a good deal, isn't it? So I would like to end my presentation with this very cute mushroom iceberg I saw last year in Antarctic. It is amazing. All right, thank you so much.